All right, good morning, everyone. If you can't hear me, let me know. It sounds pretty loud. I'm David Butler. I'm at the University of Tennessee. Been there since June. I have kind of a varied background, but I guess you could call me a soil scientist if you call me anything. At UT, I have a 75% research, 25% teaching appointment. So I don't know many of the agents in Tennessee. I've met a few of you I see out there. So how many agents do we have from Kentucky today? Put your hands up. Okay, a few. And Tennessee? Okay, quite a few. All right, I have some handouts going around. Tim and Annette are sending those around. Apologies, I think I only made enough for agents. There are about 35, so if there are a few extra, pick those up. I was kind of putting this talk together yesterday, pulling from some lectures I made for my class. So it's really long. I'm not going to go through all of it. I thought some of that information there at the end, especially on cover crops, would be just a good summary of cover crops for you. If we have time, we might get into that, but I don't think we will. The other thing is I kind of talk a little fast, so feel free to jump in, ask question. Even if it's not related to the material up here, that's fine. Just ask me. We'll have a little discussion here. One of the things I've also sent around are some soil test results. We'll be talking about those in a little bit as well, so keep those handy. All right, so what I'm going to talk about today. It's kind of a hard act to follow, but I am going to talk a little bit about the National Organic Program standards for soil management. Then we're going to talk about soil quality and mostly talk about how soil organic matter affects soil quality and building soil organic matter. Then we're going to talk about soil fertility, mostly just NPK, not get into so much the secondary and micronutrients. Talk about soil testing. As I said, you have the soil test reports. And then cover crops we're probably not going to get into today, but I think we have a talk this afternoon about cover crops. But again, the material's there. I think it'll be a good introduction for you. All right, so where do we start? Soil management for organic production. Mike already talked about this, but all inputs must be approved substances. In general, natural products can be used unless they're otherwise prohibited. An example of this would be sewage sludge, if you call that natural. Synthetic products cannot be used except unless there is an exception. Michael talked about this. Examples would be like a soluble boron product if you have a soil test that shows you need boron. Although that's a bit of a problem too, as we'll get into when we get to the soil test report. All right, the National Organic Program has 5 soil fertility and crop nutrient management practice standards. I have kind of combined the last 2 and simplified them for you. But the first here, A, select and implement tillage and cultivation practices that maintain or improve physical, chemical, and biological condition of the soil and minimize erosion. So physical, chemical, biological condition, minimize erosion. We're just going to call this the soil quality standard. B, manage crop nutrients and soil fertility through crop rotations, cover crops, and the application of plant and animal materials. Simple enough, this just talks about managing soil fertility in organic systems. The third, manage plant and animal materials to maintain or improve soil organic matter content, which we'll talk about, in a manner that does not contribute to contamination of crops, soil, or water by plant nutrients, pathogenic organisms, heavy metals, or residues of prohibited substances. Animal and plant materials include, but first we'll just call this the food safety standard related to soil management. So what materials can you apply? You can apply raw animal manures, which was already covered, but they must be composted unless they are applied to a crop not for human consumption, incorporated into the soil 120 days prior to harvest of a crop with the edible portion in contact with the soil or soil particles. I typically say this 120 days is for vegetables and small fruits. I don't know if Michael would agree. And then 90 days prior to harvest for a crop where the edible portion is not in contact with soil or soil particles. I think orchard crops, grain crops here. This goes on further. Composted plant and animal materials can be applied as long as you meet those standards. Initial carbon to nitrogen ratio between 25 and 40, temperature 131 to 170 for 3 days, as long as all of the material reaches that temperature during those 3 days. And also uncomposted plant materials can be applied. And then D, And D is a producer may manage crop nutrients and soil fertility to maintain or improve soil organic matter content. Same thing, does not contribute to contamination of crop, soil, or waters. Can apply. Synthetic substances that are included on the national list, the example of this would be micronutrients with a documented need. Mine substances of low solubility, rock phosphate, lime. Mine substance of high solubility with conditions. An example of this would be Chilean nitrate, which you can only apply up to 20% of the crop nitrogen requirement. Ash from burning or plant or animal material, but with conditions. And a plant material chemically altered by manufacturing if it is listed on the national list.
Excuse me, the restriction on Chilean nitrate?
20% of the crop's nutrient requirements, nitrogen requirements in a season. So we'll just call this the exceptions and integrity clause. And the same thing with E. A producer must not use any fertilizer or composted material containing a prohibited synthetic substance. Example of this would be some mushroom compost where they're adding urea in their compost process. Would not be allowed. Sewage sludge, as I mentioned, and burning for disposal of crop residues unless that's used for disease suppression or to stimulate seed germination. All right, so now we're going to talk about soil quality. Before we go on, were there any questions on that NOP standard for soil management?
I have a question.
Yeah.
What about a crop that's not grown organically used as mulch, like a straw?
Yeah, that would be fine. Yeah.
But synthetic in the compost is not.
Right. Well, the straw could be used for the compost, though, as well. You see what I mean? You're not amending it. You know, if you're straw, you're not mixing it with a synthetic substance, even though it was grown that way. Gray area, yeah. Okay, so just a quick review here. This will kind of help us as we go through soil quality, I think. But soil is composed of 4 parts, as I'm sure you're all aware of. You have the mineral solids, the sand, silt, and clay. And these mainly consist of oxygen, silicon, aluminum, iron, and then the important ones for our purposes, 3 secondary micronutrients, calcium, or 3 secondary macronutrients, calcium, magnesium, and potassium. That's about half the soil volume. You have water or a soil solution, which is about 25% or more, depending on the soil. Air takes up about the same proportion. And then you have soil organic matter. Smaller proportion, generally 1 to 6% in agricultural soils. Soil organic matter, sometimes called soil organic carbon because it is 58% carbon typically. And this contains nitrogen, sulfur, phosphorus, very important for those nutrient cycles, but also it contains all of the other plant nutrients, which you would expect as plant nutrients are what is going into the fresh organic matter in the soil. So soil quality, you've all heard this term. The NRCS is big on soil quality. Soil quality is just the capacity of a specific soil to function, to both sustain plant and animal productivity, maintain or enhance water and air quality, and support human health and habitation. We're most concerned about this first one, sustain plant productivity. And assessments of soil quality will focus on the dynamic soil properties. These are things that you can change with your management. We're not talking about soil texture, which is not going to change over your lifetime, but things that do change, like organic matter. While it changes slowly, you can change it with your management. Soil structure, bulk density, water, nutrient holding capacity. And of course, others are all affected by the soil organic matter. So thinking about soil quality to sustain plant productivity, here are things that soils do that sustain plant productivity. The first being provide nutrients in appropriate time, space, and form. Retain water in sufficient quantity and appropriate energy over time. So providing nutrients, providing water. Provide a network of pores to support plant root growth. Supply oxygen, remove carbon dioxide and other toxic gases. Support plant growth promoting microorganisms. And of course, provide rooting depth and physical support. And all of these, except maybe the last, are greatly influenced by soil organic matter. So let's just talk a little bit about soil physical properties and how they're affected by soil organic matter. We'll talk about soil physical properties, soil chemical properties, soil biological properties. Soil aggregation is strongly impacted by the presence of soil organic matter. Aggregation is just the formation of soils into a granular structure and the resistance to breaking apart by water. The greatest role of organic matter is to bind smaller aggregates of soil into larger aggregates of soil. So this has a big effect on soil structure. Soil water availability. Soil organic matter, of course, directly absorbs water, but then it also enhances the aggregation, which provides that pore network for water to move within the soil. Soil chemical properties, nutrient uptake and release, which I mentioned. And this is most important for nitrogen, phosphorus, and sulfur. Nearly all the nitrogen occurs in the soil as a constituent of the soil organic matter, large proportions of the phosphorus, and also most of the sulfur as well. Even in conventional systems, most people don't realize this, but most of the applied N actually cycles through the soil organic matter prior to plant uptake. Another function of soil organic matter would be microbial enhancement of nutrient availability. This, we're talking about things like nitrogen fixation through legumes, free-living bacteria, mycorrhizal fungi, which associate with plants and help take up phosphorus and also water, and also micronutrient chelation. The soil organic matter helps to bind the micronutrients into chelates, prevent them from being tightly bound into soil minerals, and subsequently this makes them more available to plants over time. Cation exchange capacity, this is strongly controlled by the soil organic matter as well as the clay fraction. This is very important, especially in coarse textured and highly weathered soils that we might have in this area, thinking more the highly weathered soils, one-to-one clays, where organic matter can greatly build your cation exchange capacity. And this is just the capacity for the soil to hold on to those cations, potassium, magnesium, calcium. Anion absorption, also important, especially for phosphorus, which is an anion, and it helps it to be more available in acid soils when you have greater soil organic matter. This is because the P gets bound up in the organic complexes rather than bound to iron or aluminum oxides and unavailable to plants. Provides a pH buffering effect and also provides some plant growth regulating substances. And then finally, the soil biological properties. Soil organic matter is the raw material for all the biological activity in the soil. We're talking about the microbial biomass. This provides, of course, labile, carbon, nitrogen, phosphorus, sulfur, and also a sink for those nutrients in the soil. The microbial biomass helps to transform nutrients into that form needed by plants that we talked about, which was a function of soil. Helps to weather minerals, release the calcium, the magnesium, and the potassium from the primary minerals. Influence the aggregation of the soil. We talked about soil organic matter doing this in the physical properties, but also the biological properties. Things that the microbes are releasing, different compounds help to bind those aggregates together in the soil. And then also the microbial biomass. In general, you have some antagonists to plant pathogens and parasitic nematodes as you have greater soil organic matter, just because you have a more varied, more biodiverse soil community. And then also things like the macrofauna, the earthworms, the soil insects, beneficial nematodes, etc. These play a role in cycling carbon and nutrients through the soil as well. So all of these things are greatly impacted by soil organic matter, and it has a lot of positive effects in our agricultural systems. But how do we manage soil organic matter? And what this diagram is just a representation of the carbon cycle. And as you all have probably seen a representation of the nitrogen cycle, which is coming up in a little bit, this is very simple compared to that. So let's just take a brief minute to look here and see how carbon is cycling in the soil and how we can use that to manage soil organic matter. The main thing to look at here, how does carbon enter terrestrial systems? By photosynthesis. Carbon dioxide comes into plants. They incorporate it into their tissue, into carbohydrates. They release a little bit back in respiration, but they're taking in a lot of carbon into their leaves, into all their biomass, into their roots, which are already below ground. And as they die, that carbon is put back into the soil. So you're building soil organic matter because the carbon dioxide is coming into the plant, going into the soil, over time, we're building soil organic matter. But at the same time, there are two main ways which carbon is lost from our soil. The first being erosion, which makes a lot of sense. You're losing soil particles, the soil organic matter is going with it, the soil carbon's going with it. But the other is soil respiration. And by soil respiration here, we mean the respiration of those microbes living within the soil. So how do we manage that? First, there are some environmental factors that affect this. The first being climate. Temperature and rainfall affect soil organic matter. So you're going to see different patterns of soil organic matter depending on your climate. Generally, with higher temperatures, you have less accumulation of soil organic matter just because it breaks down faster. There's higher microbial respiration in greater temperatures, so you have more soil respiration, losing more carbon from the soil. Rainfall, same thing. You do have more decomposition with rainfall, but at the same time, you also have much more biomass, which generally overrides this effect. So high rainfall, cooler climates are going to have the highest soil organic matter. Soil texture, greater soil organic matter in fine textured soils. This is just because the organic matter is more protected in a fine textured soil than in a coarse textured or sandy soil, where there's a lot of oxygen in the soil. It increases soil respiration again, lose more carbon. So how can we use that to manage soil organic matter? I mentioned erosion. How can we reduce erosion? Utilize conservation tillage practices, which you're all familiar with, maintaining cover of the soil by residues. There's also a lot of options to reduce tillage. Not going to get into that today, and I don't know if anyone else is. But in general, the more we can reduce tillage in organic systems or any system, as well as maintain cover of the soil surface by residues, the better we'll be in terms of soil organic matter. Utilize cover crops, which I think we'll be talking about a lot today, and also incorporate perennials into the system. If the perennial's there, obviously you're not tilling. Perennials have an extensive root system. There's going to be very little erosion under a perennial crop. And now soil respiration. This is maybe not as easy to conceptualize how soil respiration can be managed to affect soil organic matter. But basically the two things here, reduce tillage and soil disruption. More tillage, you're mixing that soil organic matter, you're providing access to it, to all those soil microbes. They're breaking it down, increasing soil respiration. Also, not a problem in organic systems which don't have synthetic fertilizers, but in general, synthetic fertilizers, which are highly soluble, will also increase microbial respiration and can lead to a loss of soil carbon. And then also drainage and landscape position affect soil organic matter. I believe my slide was out of order there. Sorry about that. But this was supposed to be back with the climate slide. Just some more factors of the environment that affect soil organic matter. You're typically going to see greater soil organic matter in lower landscape positions on a farm than higher landscape positions. Greater soil organic matter in soils that developed in grasslands. This is why we see such high soil organic matter in the Midwest. And you can use this kind of as a management tool as well, because if you think about that, these great levels of soil organic matter developed in grasslands, why is that? The main reason is that grasses have continual root turnover. Roots are dying, but they're staying in the soil, decomposing, adding to soil organic matter. And then as we think about adding more carbon to the soil, we've talked about not losing carbon, but how can we add more carbon to the soil? First would be to maximize plant productivity. Always have cover crops out there wherever the soil is bare, just to increase that intake of carbon dioxide from the atmosphere into the soil. Also incorporate perennials, as we've talked about. Conserve crop residues. Those crop residues have a lot of carbon, so if we can leave those on the soil, the better we'll be for building soil organic matter. And then also recycle local, I put waste in quotes here, but recycle local waste, utilize compost and manures where it is feasible to help build soil organic matter, or maintain soil organic matter at least. One problem conceptually that people have is I'm trying to build soil organic matter, but at the same time, those residues that I'm applying that have that carbon are what I need to supply nitrogen, supply phosphorus to my plants. So we kind of think about this as creating this steady burn situation in the soil where we're not having very fast mineralization of nitrogen, moving from an organic to inorganic form, but rather it's kind of a steady pace for plant uptake, not having a mobilization of N where we have high carbon to nitrogen ratio of residues. These are just very dry things like sawdust, for example, would have a high carbon to nitrogen ratio. If applied to the soil, it's going to tie up nitrogen. So we kind of think about residues that have a 25 to 30 range are kind of best to both build soil carbon and to supply nutrients to the crops. A good growing cover crop mixed with a grass and a legume would probably have a CN ratio about 25 to 30. And I believe I have a slide a little later getting into more carbon to nitrogen ratios. The other option would be to incorporate high residue crops in the rotation. Generally, grasses have high residues compared to other crops. And root biomass, again, plays a very important role because of that continual root turnover. And also, it's already well distributed in the soil without tillage. So you have a lot of carbon going into all aspects of all portions of the soil without having to till it in there. All right, so do we have any questions on the soil quality, soil organic matter, any of that? We're going to get into a little more practical here with soil fertility in a minute. Okay, so soil fertility. Let's just leave that slide up there. But those of you who have the soil test report, go ahead and bring that out. I know we have a lot of agents in here. Maybe just a question for you. How difficult of a time do you think farmers have interpreting soil test reports? Just in general. Easy, hard, in between? Hard, okay. How about you all personally? Easy, hard, in between? Okay. So say an organic farmer comes to you with this soil test report, and they want to know how much nitrogen is my soil going to supply to a tomato crop. You all have the report there. What would you tell them? Okay, very good. Okay, there are some nitrogen recommendations actually on that paper at the bottom. Where do those come from?
Hopefully research.
Okay, they do come from research. But say a conventional farmer has a soil test report and he's growing tomatoes. An organic farmer with a different soil has a soil test report and he's growing tomatoes. Will the nitrogen recommendation Okay, but what was the first part that you said there?
It's going to be lower because it's certified organic. Certified organic.
Okay, so you're saying the nitrogen need is going to be lower on an organic farm.
The recommendation will be lower because of that, but hopefully as the biology in place and biological activity will give more organic matter over the season than a chemical farmer is going to get from the same residue.
Okay.
But how am I supposed to make that determination from this?
Right, you can't. That's my point. The recommendation that they give each farmer will be the same. They're just giving anybody with a soil test that does a soil test, they want to grow tomatoes or any other crop, they say this is how much nitrogen you need for that crop. So we're going to talk a little bit about that. So I think a lot of farmers, especially, have switched from a conventional system into an organic system. They have this mentality. They've gotten their soil test reports. They do everything that the university tells them to do soil-wise. They're doing their soil test reports. They're applying what the recommendations tell them. Say they're applying ammonium nitrate. They're applying, 120 pounds of N per acre. They come into you. They've switched to organic. They want to apply They're thinking, what do I have to apply to get the same amount of N? I want to follow the soil test report. What do I do?
Get me a report on your organic matter.
Okay. Organic matter or organic amendments or both those? Okay. Okay.
Your fertilizer.
Okay. All right. These are all very good. So we're going to keep going with this. I'll run through a few slides and maybe ask you a few more questions here. But in organic systems, as I mentioned, we think of it more as a systems approach. We're talking about the soil biology, the soil chemistry, soil physical properties. It's not so much we're just trying to replace those synthetic inputs that we're used to if we are coming from a conventional background with organic inputs, but rather we have to shift this management to a whole systems approach where we realize that all those organisms in the soil are different crops that we have out there. All of that's going to affect how much nutrients we have for our following crop going through our system. And also, how can we manage this system then to optimize our fertility over time? We may understand what's going on, but how do we then manage that system? So as I mentioned, the carbon cycle is pretty simple compared to the nitrogen cycle. This is a conventional nitrogen cycle, and I've just X'd this out here. 3 ways that nitrogen comes into terrestrial systems. One that we do not use in organic systems directly would be inorganic nitrogen from industrial fixation. But we do get atmospherically fixed nitrogen from legumes. As we talked about, legumes form a symbiotic association with rhizobia bacteria, and they can take nitrogen in from the atmosphere and fix that into the soil. There are also free-living nitrogen-fixing bacteria as well, a little bit harder to manage, so we don't talk as much about those. And then also, all systems would have wet and dry deposition of nitrogen that's fixed by lightning. That's relatively small, maybe 10 pounds per acre per year, but it's also there. Before I go on, let's just talk about some other transformations that we have in the nitrogen system that are important to think about. So we have the fixation coming in from, say, lightning or legumes or other nitrogen-fixing bacteria. And then we also have recycling of residues, dead plant matter, animal manures, and all of that as it dies, as it's added to the soil, it's going into the organic nitrogen pool, which is represented down here. So when you have that organic nitrogen pool, the soil microbes start to work on that. They mineralize it into the ammonium form, and then other bacteria take it from the ammonium form into the nitrate form, and both of those are readily uptaken by plants. You can lose some with nitrate leaching. Not as big of a problem in organic systems because you don't have a lot of nitrate at any one time out there. And these are taken up by your plants. You can lose some as well through denitrification or volatilization of ammonia. I don't even see that there. There it is. So in general, that's your nutrient cycle in organic systems. The ammonium can also go back, be immobilized back into organic nitrogen. As I mentioned, say you add a high carbon residue, the microbes need nitrogen to process that carbon. They take up ammonium from the soil, taking it away from the plants. But I think these are all concepts that you are relatively familiar with. As I mentioned, in organic systems, we mostly rely on both the atmospheric fixation of nitrogen and the biological. Biological, much more important because that's something that we can manage. It's about 70% of the global nitrogen fixation. As I mentioned, rhizobia form symbiotic associations with legumes. This is alfalfa here, nodules in the root of alfalfa. There are also some non-legumes that do this, but none of those are agriculturally important that I'm aware of. But then also there's a lot of free-living nitrogen-fixing bacteria in healthier soils that have a lot of organic matter. Some of the more important ones are Azotobacter or Azospirillum. These are hard to manage, though there are some inoculants out there on the market for these free-living nitrogen-fixing bacteria. But there's a lot of research to be done there. But in general, they're also adding nitrogen to the soil. So just keep that in mind. Okay, so somebody talked about organic matter relating to how much nitrogen was required. So what is our general assumption for the mineralization rate of soil organic matter? Go ahead and look at the soil test report there. What is our soil organic matter range on these samples that I've shown you? There you go, 1.5 to 2.2. So we'll just say 2% as an average there. Our general assumption is that about 20 pounds of N per acre per year will be mineralized from 1% of soil organic matter. This is a little bit conservative. Maybe it can be up as high as 40 pounds of N per acre, but probably 20 to 30 is what we would typically see. So for soil of about 2% organic matter, this is in the plow layer or down to 6 inches, we would expect a release of about 40 pounds of nitrogen per acre per year. And as I mentioned, this is just an assumption and a generalization. This is going to depend on temperature, precipitation, aeration, management. Aeration meaning how aerated your soil is. So at the same time, we have a lot of National Organic Program allowed N sources. This is a common question I get. What can I apply to, what kind of nitrogen can I apply to my plants when I need nitrogen? Mostly we're going to focus on the first three. Manures, very economical if there is a local source. Compost and other residues from your farm. And legumes, as I mentioned. The percentage nitrogen in these will vary. And you can have organic amendment reports from your soil test lab to give you a little more detailed information here. So with manures, we have about 1 to 4% N. I have kind of an index of availability here, and I've said that the manure nitrogen will be moderately available. By this, I mean about 50% or so. Again, a general assumption, will be available to the crop in the year that it's applied. Compost and residues, however, generally have a lot lower nitrogen, and this availability is going to be very slow. Legumes, we can have from 0.5 to 4% nitrogen, just kind of depending on their growing stage and which legume you're looking at. And the availability here will be slow to moderate. I have another slide, I think, to show this later. But again, depending on that carbon to nitrogen ratio. You have a lot of other amendments here that organic farmers, I think they're pretty commonly used, I would say, but they are generally pretty expensive, so they're only used kind of to fill in gaps or an area where we're having problems. Some of these that you commonly see, blood meal, this is 12% nitrogen, so quite high, and that's rapidly available. Feather meal, another high percentage of nitrogen, 15%, moderately to rapidly available, I would say. Seed meals, these are things like soybean meal, mustard seed meal, cottonseed meal. The residue that's left over after these seeds are crushed for oil production. These typically have about 5% to 7% nitrogen. Again, moderately to rapidly available. Alfalfa meal, which can be really expensive, about 4% nitrogen, also rapidly available. Fish emulsion you sometimes see in fertigation systems. Chilean nitrate, as we talked about before, there are restrictions there to only 20% of the crop's nitrogen requirements. And then a lot of other animal and plant residues. Another thing to mention here, these sources, the blood meal, the feather meal, the seed meals, these do not need to be from organic livestock production. The seed meals actually do not even need to be non-GMO currently, although that might change in the future. So any questions on any of this material?
I'm wondering, with your 2% organic matter soil, 40 pounds of nitrogen per acre, if you were going to write up a recommendation for tomatoes for that soil, what would you how much nitrogen would you recommend?
Well, that depends. Maybe we have to go a couple more slides here, but it'll just depend on their management as well. So you have the soil organic matter. That's one portion. So you want to assume you're going to get 40 pounds of N contribution from that soil organic matter. Maybe they also had a crimson clover cover crop out there the season before. You can estimate how much nitrogen is in that crimson clover and it's going to be supplied, depending on how they're going to manage that. They may have applied, that's actually the next slide, they may have applied manure last year or the year before that, and that's still going to be contributing nitrogen to that crop. But these next two slides will help us with that. As I mentioned, legumes. These are just some common legumes used in this area. You have cowpea, which are a warm season legume, crimson clover, hairy vetch, cool season annual legumes, red clover and white clover, which are perennial. Red clover is more of a biennial legume. And most of these legumes are going to have a nitrogen content of about 3 to 3.5% at flowering. And what this means is a carbon to nitrogen ratio that's pretty low, about 13, if we assume that 40% of the plant tissue is carbon, which is a good assumption. So these are going to mineralize fairly rapidly in the soil because of that low carbon to nitrogen ratio. Again, it's below that 25 to 30 range that I talked about. Below 25 to 30, you're going to have a nitrogen release. Above 25 to 30, nitrogen is going to be tied up in the soil. However, the nitrogen availability to that subsequent crop can be variable depending on when the cover crop is terminated. Legumes, we're going to be much closer to 50 or even higher. Grasses or grasses mixed with legumes are going to be lower than that. And this, just like mineralization of soil organic matter, is controlled by an interaction of factors: environment, management, quality of the residues. In general, again, higher temperature, higher moisture, more aeration, it's going to mineralize faster. Incorporation is going to mineralize much faster than mowing or rolling and leaving on the soil surface. Tissue quality, higher carbon to nitrogen ratio will mineralize slower. Higher lignin will mineralize slower as well. I think I've covered this, but here's my slide on carbon to nitrogen ratio. Generally, with a high carbon to nitrogen ratio, again, greater persistence as a surfer mulch, but slower nutrient release. But you may want to manage as a persistent surface mulch to suppress weeds at the same time. So just kind of some things to keep in balance. In general, we'll have greater carbon to nitrogen ratio with grasses, then broadleaves, and then legumes with the lowest carbon to nitrogen ratio. And this increases with plant maturity as well. As that plant flowers, it starts to move carbon into the root, move nutrients into the roots and things, so we get a higher carbon to nitrogen ratio as it dries out, gets older. Lower carbon to nitrogen ratio, we have that greater release and breakdown, but it's not going to persist on the soil surface, and it's unlikely to tie up soil nutrients when we have that low carbon to nitrogen ratio, and we'll typically release nutrients to the soil. So residual N mineralization. We've talked about mineralization from soil organic matter. We've talked about mineralization from organic amendments. We've talked about mineralization from cover crops. How about residual nitrogen mineralization? And this is just an example that I worked up here. This is for, say, a broiler litter application of 4 tons per acre. We assume that there's 2.5% N in that broiler litter, which is a good average. So this would be applying 200 pounds of total nitrogen per acre. In the first column here, well, let's start over here. I have years going down the side, so 1 through 5 years. In the second column, I have the amount of nitrogen mineralized, that is the inorganic nitrogen released from the organic nitrogen, in pounds of N per acre in a single application. So this is one application of broiler litter at 4 tons per acre in year 1. And we're assuming that about 50% of that nitrogen is going to be released in the first year. So if you apply, say, late winter, early spring, 4 tons per acre broiler litter, 200 pounds of N per acre, you can assume that 100 pounds of N will be released during that year. But I think the part that gets a little confusing and that people often forget about is that that extra 50% is typically still there. You might lose some with volatilization when you apply, but typically the rest of that is there. It's being incorporated into the soil organic matter. It's sticking around in the soil. It's just taking longer to mineralize. So generally we would say about 8% more of that's released in the second year, 5% in year 3, then 2, 1% in years 4 and 5. So where this starts to get a little more interesting is, say, the second column we apply 2 years in a row. The first year we apply that 200 again, but then we come back and we apply another 200 pounds of N per acre in the second year. But in this case, you're getting more nitrogen because of that residual release of nitrogen. So you have 100, 116. You stop applying. You still have 26 pounds of N per acre in year 3, 14, 6. And then finally, just this last column here is what if you continually apply year after year after year the same rate? The first year you only got 100 pounds of N per acre, but then you're getting 116, and that's moving up slowly over time because you continually have that residual nitrogen release over time. So you may think you're just getting 100 pounds of N per acre when you're applying here again, just like you got in year one, but you're actually getting about a third more than that. So back to the question on the tomatoes. You have the soil organic matter, 40%, or say 40 pounds of N per acre. Say they applied chicken litter last year. Maybe you're still getting, let's say, 20 pounds of N per acre from that. You're up to 60 pounds of N per acre. They have a crimson clover cover crop that was really good. Let's say it's, let's make it easy. Let's say that was 160 pounds total N from that crimson clover cover crop, really good cover crop. Half of that's available in the following year. So what am I up to? 80 and 60, 140. You're pretty close to the tomato recommendation already. Okay. Just briefly on phosphorus, as you all know, a lot of agricultural soils have ample P, total P, due to a history of manure and fertilizer application, mostly because there's an imbalance of nitrogen and phosphorus when we apply manures to the nitrogen needs. There's a much greater percentage of phosphorus than the plants need. Plants need phosphorus in, say, they need about 1 part phosphorus for every 8 parts nitrogen, whereas manures are about 3 parts nitrogen to 2 parts phosphorus. So there's a lot of leftover phosphorus when we apply manures to meet nitrogen needs. However, this availability of P is limited due to soil minerals, especially here in the southeast. pH, lower pH, we have adsorption to iron aluminum oxides in clay soils. Higher pHs, which isn't so much of a problem here, but we can have precipitation of calcium phosphates. So in general, phosphorus availability is greatest around 6.5 pH, which is generally what we would shoot for with most crops anyway. In organic systems where we can apply inorganic phosphates, we have a few solutions that we can use without applying more phosphorus. One is to use phosphorus solubilizing cover crops, things like buckwheat and lupins or lupines. These cover crops secrete organic acids in their rhizosphere just from their roots. So this helps to solubilize P and make it more available to following crops. As we increase organic matter, as I mentioned earlier, that phosphorus gets put into that organic biomass. So as it cycles through that biomass, it's more likely to be available to plants. And then also encourage mycorrhizal fungi. Obviously, we won't have any fungicides in organic systems other than a few things like copper sulfate, and also reducing tillage can encourage mycorrhizal fungi. Mycorrhizal fungi I may have mentioned, but that's just a symbiotic association of a fungi with plant roots, and that fungi helps the plant to take up more phosphorus. So a few National Organic Program P sources here. As I mentioned, broiler litter has quite a bit of phosphorus compared to the nitrogen. About 2.5% if we're thinking of it as we get bagged fertilizer in P2O5 fashion. So that's pretty high, and the availability is also going to be moderate to high because it is an organic source. Compost and manures are going to be a little lower, but not always. These could still be kind of high. And unlike the nitrogen, the P in a compost or in a fresh manure is going to, the phosphorus is going to be about the same level of availability. You also have things like rock phosphate or phosphatic clays. These are mined substances. Generally, the availability here is very low, although they do have high amounts of phosphorus in them. You also have some animal slaughter residues, things like bone meal that has a high phosphorus content, and this is moderately available. This is used a lot in, say, seed starting mixes where you want some soluble phosphorus up front. Alfalfa meal as well. Some of the other organic nitrogen sources are also going to have some phosphorus. About 3% sp2O5 in alfalfa meal. And then other plant residues, animal byproducts and things are usually going to have some level of phosphorus. And those amounts are out there, but they're not so important. I can't think of a lot of cases where you would need more phosphorus than what is provided by that up there. And then finally, I'm going to talk a little bit about potassium. There are naturally high levels of potassium in soils. As I mentioned, they're part of the primary minerals in soils. Very high amount, just to kind of give you an idea, there's about 50,000 pounds per acre in a clay loam soil. That's a lot of potassium. But much of this is fixed in the primary minerals. Potassium feldspar and mica, 90 to 98% is fixed. Very, very slowly available. Only available through weathering over time. It was actually once thought that because there was so much potassium in soils, it would always weather fast enough to meet crop needs, but that's not the case. You have some potassium in non-exchangeable sites in between clay mineral layers. This is a little bit more rapidly available than that's fixed in primary minerals, but also very slowly available. Soil microbes help to release this over time, and also just natural weathering processes. And then you also have the exchangeable potassium, which is most available, but this is only about 1% of that total phosphorus. Total potassium, sorry. And then again, just another chart showing potassium sources and availability. Potassium doesn't act like phosphorus in the soil. If it's there, it's generally highly available if it's not fixed in those clay minerals. Manures as well, about the same percentage of potassium as K2O anyway, as N and P. Compost, plant residues are a good source of potassium. Seed residues, those seed meals that I talked about is what that means. Wood ashes, which is where we get the name potash, 10% potassium as K2O, and this is rapidly available. Green sand, you sometimes see advertised for use in organic systems. The thing to remember here is this is very, 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 very slowly available, kind of like primary minerals. It only is available with weathering over time, the potassium in green sand. This is just a mined material. It comes off the coast of New Jersey, Delaware is where that's mined. Potassium sulfate and potassium magnesium sulfate, these are also mined materials, high potassium content, high availability. However, these have to be, again, like I said, a mined source, but no further chemical processing other than sieving, grinding, etc. Okay, back to the soil test report. Do I have any time left? No? Okay, one quick thing then. Look at the soil test report, and somebody tell me from this soil test report, let's just use, I think you have sample A as the first one. Let's just say on that, can someone tell me how much phosphorus in pounds per acre is available to the crop based on that soil test report? This isn't actually it, sorry. This is a soil test recommendation just for tomatoes in general. Anyone want to go out on a limb? What does this, just tell me then, what does this soil test report tell you about the phosphorus in the soil? I can bring it up on the screen. 1 second. I think so. Okay, so hopefully you can see this. Got the phosphorus right here. I don't know why that keeps popping up, but we can see it anyway. Here we have the phosphorus soil test report. For each, so that's in the third column over, as you see on your soil test report. What does that say? Can you, someone interpret that for me?
29 pounds of phosphorus.
29 pounds of phosphorus per acre. Okay. What does that mean?
That there are 29 pounds of phosphorus there. The lab don't know whether it's an organic or anything about how.
Okay, so what does it tell you?
For tomatoes, it's going to need some phosphorus.
Okay, if you didn't have the interpretation down there on the ignore the second part. Okay, ignore the recommendations. If that says 29 pounds of P per acre, say your tomato needs 60 pounds of P per acre. Does that tell you anything?
And I need about 30 pounds of P.
How many of you would agree with that? So you all disagree? No? How many disagree? Oh, sorry. So he said if there's 30 pounds of P on your soil test report, and I'm asking, say, for example, you have a crop that needs 60 pounds of P per acre, what does that mean in relationship? And he said, well, possibly that means that you need 30 more pounds of P per acre for your crop. So would you all agree with that? Does someone disagree with that? Most agree? Okay, this is a common misconception, so don't feel bad. I actually wish they wouldn't report these as pounds per acre. Keeps coming up because this has nothing to do with how available it is to your crop. These are only meaningful if they're researched over time, many sites, seeing how crops respond to that amount of phosphorus in the soil. P plants can take up. How much P is cycled through the microbial biomass over time. It really doesn't have that straight relationship that you would think it should. You might think it does, but it just doesn't. So this says 30 pounds of, say 29 pounds of P per acre. The only thing that's important for your purposes are this rating, where it says medium, low, medium, low. Once you have that information, medium, low, high, you can go to the research results, which is what I had up here. The soil test recommendations. You know your phosphate is low. This says for tomatoes you need 240 more pounds of P per acre. That's the only thing that soil test tells you. It's not the straight-on pounds of P per acre that is actually available to the crop. It does not mean that at all. So just want to put that out there. It's a common misconception. A lot of farmers have that misconception, so kind of helps to educate in that regard. So I think I'm out of time. Do I have any other questions? Yeah.
I get questioned frequently about the use of those other materials that you cited, such as poultry litter, blood meal, and things like that. And people are concerned about the nature of those off-site materials because of the intensity of management that is applied to the production of broilers, for example.
Yeah.
And they say to me, well, you know, what's the point of applying natural materials like that if the usage of those materials, if the production of those materials has so many other things that we're concerned about?
Right.
That's to me one of the conundrums that we have in nutrition management in organic systems.
Yeah, that's a really good point. The comment was regarding the use of broiler litter, blood meal, et cetera, that comes from conventional production of livestock. This is a growing concern. There are a lot of organic farmers that actually don't support the use of those products from conventional operations. Probably over time, as it becomes more possible, that will be phased out of the organic, what is allowable in organic production, but probably not in the foreseeable future, just because we do have those difficulties managing nutrition without those recycled wastes. But no, I think that's a very good point. And also, I think the same point could be made for the use of GMO seed meals or manures from livestock that have been fed GMOs, et cetera, antibiotics, and those things. So, good point. Any other questions?
I don't think
Out of time.
Out of time. Thank you, David. Round of applause. Are you going to be